Welcome you all in this new video, and in this video we are going to discuss a very interesting topic, okay, that is escape velocity. So this is very interesting topic. This is regarding the earth phenomena, okay. So we know that whenever we throw any particle in the air, that always comes back like this, okay, in a projectile motion, we can say, okay, projectile motion, okay. So whenever we throw any particle from the surface of the earth, okay, that always come back like this. We always see this thing, okay. So many times we think that why this is so, what if and what is the condition that if we throw something that will go, beyond the reach of that earth magnetic field, means that will never come back. So what is that condition? So guys, that condition is escape velocity, and in this video we are going to discuss about this topic, okay, escape velocity. Within the 5-6 minutes of this video you will easily understand what is this escape velocity and what is the relation, okay, what is the expression for this escape velocity, okay, so that from that expression you can derive any planet escape velocity. Means in any planet you throw something that will go beyond the reach of that planet or that object, okay, beyond the reach of that gravitational force of that particular object, means that will never come back to that object. Simply we can say escape velocity is the velocity if we throw anything with this velocity, okay, upward. Like this is earth and I am standing here and I throw a particular, I can say particular thing like this, okay, upward with this velocity, okay, and that thing will never come back. It means that that will never fall again in the surface. Means if I throw that thing with this velocity, that will go beyond the reach of gravitational force of earth, okay. So this is escape velocity, okay, and in this video just within 4 and 5 minutes you will easily understand what is the expression of escape velocity. Not even earth, you can derive expression or derive the value of escape velocity any kind of the product, any kind of, you can say, planet, okay, any kind of the, you can say, object, whatever is the size of that object, okay, you can easily calculate that thing, okay. So let's start our video. So let's suppose that this is your earth, okay, let me change color, okay, this is your earth. So first of all, understand the concept, okay, this is your earth, okay, and I am, let's say I am standing here, okay, and I am standing here, let's say this is the, we are assuming that this is the region, okay, through which the gravitational pull of the earth is. There is no any particular limit, okay, we can say that gravitational force, as we know, is the weakest force. We are assuming that this is the point, okay. So let's suppose I throw a particular object from my hand to upward like this, okay, and that object never come back, okay, that object never came back. It means I throwed that, okay, that object with the escape velocity. Escape velocity, as its name indicate, that escape means it is escaping from the gravitational pull of the earth, okay. So I am supposing that I throw a particular let's say stone, okay, from my hand upward and with the speed of escape, okay, with the escape velocity, okay, so that will never come back. Okay, here we have to understand how we can derive the escape velocity, okay. So let's suppose that, okay, your escape velocity, what is the work done, okay, that when I am throwing that stone from here to, let's say, it point A and this point is B. B is the point where that object or that stone became very free from the gravitational pull. Means A is the point from where I throw that, and B is the point where there is no any influence of the earth magnetic field. Means at that point the stone will never come back to the earth, okay. So let's suppose that what is the work done. Let's say stone is here, okay, this is the stone at the point of B. Let me change the color so it will be easy for you to understand. So this is the stone and this was the initial position at A, and B is the final position of the stone. We are assuming at any instant of time t, okay, this is not fixed, okay, this is, we are assuming a particular instant of time t, okay. So now we have to understand how we can derive, how we can calculate what should be the escape velocity. Easy. First of all, we have to understand work done. Okay, work done. How much work is done from here to A to B? Okay, that work done will be equal to your kinetic energy, means the energy that is acquired by this object A, okay, while it is moving from A to B. Okay, this is the stone, okay, red stone. And what is the kinetic energy it has gained when it travel from A to B? Okay, because it is motion, and whenever a thing is in motion, we always include the kinetic energy. Okay, so it means that we have to equate work done. Okay, what work done means? Work done is always in the negative because force is inside. Okay, work done is what? And from where we can say that work done is what? Work done is means gravitational force between that, gravitational force between them and distance. Okay, let's calculate it further, so it will be very easy for you to understand very easily. Okay, so work done, how we can say, what is the work done? Work done F dx. Okay, we are assuming that it is reaching at a height of dx. Okay, we are assuming it. Okay, so and total work, if we talk about, then total work is what? Let's say this is we can say, assume that this is we can say this is the r. Okay, it is r to infinity. Okay, this is from r to infinity, and it is equal to kinetic energy, kinetic 1 over 2 mv square. What is this v? Let's say ve. This is that velocity with which it is moving because of, and when that product, that material is moving with this velocity. Okay, so because of which it is able to escape from the earth gravitational force. Okay, so now we have to, we know that what is the gravitational force between two objects, that is m. Let's say m is the mass of that, this small object that we are throwing. Okay, so and capital M is the earth mass over let's say this is x square over g. Okay, and this is equal to 1 over 2 mve square. Okay, and this is dx. This is our expression. I wrote it directly. Okay, so don't be confused here. Let me write it here again. So what is the, we know that work done is equal to kinetic energies. Whatever work done is there between A to B, okay, that is equal to kinetic energy acquired by that particle. Okay, so it will be equal to what? M me. Okay, me is the mass of earth, m is the mass of that small particle. Okay, over what is this? This is your x square dx. Okay, and this is total work done from r to infinite. R is from r, this r is the radius, and I was standing there. Okay, and here is, let's say here is a particular that infinity. Okay, we are assuming that. Okay, so I am from, I was throwing that stone from this point to this, means from the distance of radius r. Okay, of the radius of the earth. Okay, so this is expression, and this is equal to 1 over 2 mve square. Okay, so now calculate this. Me is constant. Okay, so your so you will do this thing, infinity r. Okay, so what will be the expression for you? So when you will differentiate this like this, 1 over 2 mve square. Okay, now understand here, guys. So this will be equal to what? Me, here is g also. Okay, g, me g over r. Okay, this can be equal to r square. Okay, r square means what? When you will derive, you will easily get this thing. Okay, sorry, this will be r. Sorry for this interruption. This will be equal to r. Okay, I am putting this directly here, because if I used to solve this, then it's easy, but it will take time. So we don't have time. I had promised you that I will make you understand within the 4 minutes. Okay, so this is the expression that you get. So this will be equal to 1 over 2 mve square. Okay, so m to m cancel. So now you have only me g over r. What and this is the expression, this is equal to 1 over 2 mve square. Okay, so now do further. So what was the expression? That was me g is the gravitational constant, it will be always constant. Okay, and let's say its value is 6.67 into 10 raised to power 8. Okay, and dyne centimeter square. Okay, so this is the unit. So let's say this is your me is the mass of earth and g is the gravitational constant. Let's say this is r square, and here I multiply with r, is equal to 1 over 2 m was already cancelled out, so here we have only v e square. Okay, so here we have only v e square, so this is minus 8. Okay, don't be confused. So v e. Okay, now this expression is equal to g, that is the gravitation acceleration, we can say. Okay, what is the value of gravity? Gravity means what is the acceleration induced by the earth gravitational force on a particular body while it is falling on the earth. Okay, so that is g. G means, you can say, gravitational acceleration. Okay, that acceleration is produced by earth gravitational force. Okay, so this is g and this is r. This is 1 over 2 v e square, and v e is equal to 2 g r under root. So this is our expression of escape velocity. Okay, from here we can easily derive what is the value and what is the actual value of this ve, means escape velocity. I am writing directly, you can calculate easily. Okay, r is what? Gravitation. R is the radius of that is 6 4, you know, this is the radius of earth, and gravity, what is the value of gravity? 9.81. okay, you can say meter second inverse. So by putting all these value here in this expression, you will easily get the answer. Okay, so there is kilometer per second, means what is the escape velocity of earth? That is 11.2 kilometer per second. It means you have to throw a particular stone or particular object with this velocity. That's why when you will throw the object with this velocity, that object will go beyond the reach of earth gravitational force. It means that can never be pulled back by the earth. Okay, so this is the